Today, our mathematician spotlight is Evelyn Lamb. So Evelyn is not a math professor. So most of the people I show you are like math professors. Evelyn Lamb got her undergraduate degree in math. She got a PhD in math, and now she's a postdoc at the University of Utah. But she decided that instead of just studying higher Teichmuller-Thurston theory and other things that she had been studying, what she was really passionate about was like explaining math to people. So she's actually now a freelance science writer. So I don't know if it's because of who I'm friends with, but anytime something scientific happens in the world, it pops up on my Facebook feed in Evelyn Lamb's blog post, because she writes for Scientific American. Roots of Unity blog is what it's called. So for instance, as a self-promotion, I came up with like a cool theorem once that involved running and math. And so Evelyn wrote about it on her blog. So the tagline here is, if you ran a race at an average pace of 3.07 per kilometer, did you run any single kilometer of the race in exactly 3:07? Well, it's complicated. And I know she's a really good writer because I was interviewed about this paper for like a running publication, and I really thought I was doing a good job of explaining it well. And then I read her article, and it's like 100 times better than mine. So anyway, she's really good, and she explains complicated like research mathematics in a way that people really do understand. So it's really great. Good. Okay. So for the past couple of classes, we've been talking about triple integrals and the solid regions of integration over which we integrate triple integrals. And today and next time, we're going to talk about tools for changing integrals into other variables to make them easier. So here's an example. So convert from rectangular coordinates to polar. So suppose we want to convert from rectangular to polar coordinates for a double integral. So we want to compute the double integral over the unit disk d of the function e to the x squared plus y squared dA. That's what we want. So our region of integration here is the unit disk. That is not my best unit circle, but we're just going to have to go with it. There it is. Okay. So you could either do horizontal slices or vertical slices. It doesn't matter. Let's just do, say, horizontal slices. So if we pick our favorite y value, then x goes from something to something. So x goes from something to the left to something on the right. So the way we usually do this is like write the equation for the curve and then solve it for x. So the unit circle, the equation for that is x squared plus y squared equals 1. So if we solve that for x, we get x squared equals 1 minus y squared, and x equals plus or minus the square root of 1 minus y squared. So then you might ask, do we want the plus or do we want the minus? Yes, she says. Yes, we want both. Okay, so on the left, you'll notice that x is negative, and on the right, you'll notice that x is positive. So x goes from negative root 1 minus y squared up to positive root 1 minus y squared. So if we write this as a double integral, we'll go from x equals negative root 1 minus y squared up to x equals positive root 1 minus y squared. And which of those do we want? Well, we want all of them from the bottom to the top. So I did not label my axes, but this is the x-axis and the y-axis. This is 1, negative 1, 1. So we want from y equals negative 1 to 1. And we're integrating still e to the x squared plus y squared. And now dx, because that's on the inside, and then dy, because that's on the outside. Okay, well, we are asked to compute. So let's do it. So the antiderivative of e to the x squared plus y squared with respect to x, what is it?
E to the x squared y squared divided by 2 to dx.
Yeah, you'd want to just take the same, so the derivative of e to the something is e to the something, and then if you're taking the derivative, you'd multiply by 2x. So maybe you want to have this and you want to divide by 2x. Very reasonable thing to do. The problem is if you had e to the x squared plus y squared, and then you're like, I want to adjust, like an adjustment factor of 1 over 2x. Okay, suppose that this is the antiderivative of this. That means that the derivative of this function gives me my original function. So let's take the derivative. Okay, well, when you take the derivative, you have to do the product rule. So you get all these terms. So it's not going to work out. So once again, it was a trick question. There is no antiderivative. So it's actually kind of one of the famous functions that doesn't have an antiderivative. Like e to the x squared with respect to x, no antiderivative. Just like the other day we talked about that sine of x squared with respect to x doesn't have an antiderivative. So I've given you one that doesn't have an antiderivative. This one is slightly more important because e to the x squared is the function for the bell curve. So people actually do wish to integrate e to the x squared, and you can't do it. You have to just do it numerically and get an approximate answer to as many decimal places as you want, but you can't find an antiderivative. So we can't do this because there's no antiderivative. Okay. Now we have been talking about a clever trick for computing things when there is no antiderivative, which is switching the order of integration. So suppose we switch the order of integration. We switch and we do vertical segments instead of horizontal segments. Well, maybe you can see that because everything is symmetric, we would get exactly the same thing, except that everywhere there's an x here, it would become a y, and everywhere that's a y here, it would become an x. So it's just like changing the names. Everyone just puts on a new name tag. Oh, your name was x, your name is now y. It doesn't change anything. It's still no antiderivative, and changing the order of integration doesn't actually change anything. So maybe it's not possible, or maybe we just need a new technique. The one thing you might notice is that this is a circle. Why are we using rectangular coordinates for a circle? We should be using polar coordinates. And e to the x squared plus y squared. X squared plus y squared is just r squared. It's all very natural. If this was e to the x, we might get a little concerned. Polar coordinates, that's going to be r cos theta. That's weird. No problem. E to the x squared plus y squared becomes e to the r squared. So let's convert to polar. So let's actually do this thing. So let's rewrite this. We want the double integral over d of e to the r squared dA. So I just rewrote this. X squared plus y squared is r squared. But this dA, what is it in polar coordinates? So in xy coordinates, dA is dx dy. So maybe dA is just dr d theta, but we better be careful. So let's think about this for a second. So in the xy plane, here's x, here's y. If you have a little dx, so I'm making it exaggerated, but this is a tiny infinitesimal distance dx. And up here, you have a tiny infinitesimal distance dy. Then dy times dx is the area of this little rectangle. So this is dy times dx, or dx times dy, which is dA, the area of that little rectangle. Now, in polar coordinates, you have your plane, and perhaps you have some little dr. So you've changed your radius by a little bit, dr. And then also you have your somewhere, so you changed your angle by a little bit, d theta. So again, I'm exaggerating. My infinitesimal d theta here is quite big, but it's so that you can see this region. So we want to know if we change our r by a little bit, dr, and we change our theta by a little bit, d theta, we want to know what's the area of this region, because that is dA. We want it in terms of r and theta. So I claim that, first of all, this distance here is dr. I think you believe that. That's how we defined it. It's the same all the way around. And then, okay, this is basically a little rectangle, so I'm going to say its area is this length times this length. So this width, or whatever you would call it, is dr. And then this length type thing here, we have to figure out what it is. And I claim that it's r d theta, where r is however far out you are. So the reason for that, let's go back to like basic geometry. So if you have a circle here of radius 1, and then you go around some angle theta, you might want to know what is this arc length here. And if you're measuring theta in radians, this arc length is actually just theta. This is one really good reason to measure in radians. And one way you can figure that out is by making a proportion. So theta over the total angle, so the proportion of the circle that you have, is the same as the arc length over the total length, which is 2 pi times the radius, which is 1. So I guess I could just call this 2 pi r and then solve. Let's see, theta times 2 pi r equals 2 pi times arc length. So I just cross multiplied here. I can cancel my 2 pi's. And I get theta r equals arc length. So when radius equals 1, the arc length is equal to theta. But when the radius is something else, theta times r is the arc length. So here, our theta is d theta, so our arc length is r d theta. So our dA here is r d theta dr. So that's the takeaway message, is that in polar coordinates, dA is r, and usually it's written in the other order. It's multiplication, so it doesn't matter. R dr d theta. So when we want to convert, that's what we'll use. So let's rewrite this thing now that we know. So we want to have a double integral of e to the r squared times dA, which is r dr d theta. So we want r to go from something to something, and we want theta to go from something to something. Let's see, it's the unit disk, so we want all the radii from 0 to 1. So r goes from 0 to 1, or we want all the circles from radius 0 to radius 1, and we want to go all the way around. So we want theta to go from 0 to 2 pi. Now, this is not a priori better than what we had before. We've just written it in different variables. We've given everybody a new name. Before we called x y and we called y x, and it didn't improve anything. But now we've maybe changed something, and maybe life will be better. So let's see if we can compute this. I'm going to erase my picture so that we have space to possibly compute, if we are lucky. Okay, so I'll rewrite the outer integral again. Theta goes from 0 to 2 pi. Okay, let's see if we can do this one. The integral of e to the r squared times r with respect to r. Yeah.
1/2
Yeah, 1/2 e to the r squared. Let's try it. If we take so you claim this is the antiderivative. To check it, let's take the derivative. So if we were to take the derivative of e to the something is just e to the something, so e to the r squared, times the derivative of the inside, which is 2r. So the 2 would cancel with the 1/2, and we get e to the r squared times r, which is what we have. Yes! It worked! Yay! So we evaluate from r equals 0 up to r equals 1, and we take that whole thing d theta. So let's do it. So theta is going from 0 to 1. Okay, we plug in r equals 1 here. We get 1/2 e to the 1, which is e. And then subtract off what happens when r equals 0. You might think, oh, if I plug in 0, I just get 0. But you don't. So just go slow, be careful. This is 1/2 e to the 0, which is 1. So we're just integrating 1/2 e minus 1/2 d theta. And there are no thetas in this. So, oops, this is not theta equals 1. This is 0. Theta goes from 0 to 2 pi. My bad. So we'll just get multiplied by theta, and then plug in theta equals 2 pi, and plug in theta equals 0. So this is going to be the integrand, 1/2 e minus 1/2 times 2 pi. So the halves cancel out with the 2, and we get pi times e minus 1. Hey, it worked! Amazing! And just for fun, we got something that has all of the important mathematical constants in it except 0. Amazing. 1, pi, and e, all in an expression. Hey, we did it! I'm happy you're so happy. Good. So, you might ask, like, why did it work? Like, what was it about converting to polar that worked? And the area differential with this extra r was exactly what we needed to be able to take the antiderivative of e to the r squared. We needed that extra r on the outside in order to be able to take the antiderivative. So that was how it worked. Yeah. Questions or ideas? Yeah.
Are you still able to switch the order of integration? Like, do like r d theta dr? Is that possible?
Sure. Yeah. You're welcome to switch the order of integration. Here it actually doesn't matter because the expression doesn't depend on theta at all. So you could do it anytime. Yeah. Yeah. Other questions? Ideas? All right. Well, so let's try another one. Okay. So suppose you were asked by some person to compute the integral 0 to root 2 over 2 y to root 1 minus y squared of 1 dx dy. You're supposed to compute this thing. So anytime you're given such a like some naked bounds of integration here, I suggest that you figure out what they mean. So for instance, in here, it's x. It's x that's going from y up to root 1 minus y squared. And it's y that's going to from 0 up to root 2 over 2. So I suggest just drawing that in for yourself so that you kind of know what's going on. Otherwise, it's confusing. So put that on. So the first thing to do, of course, is to draw a picture. So sketch the region. So we're going from x equals y equals, who knows what it's supposed to look like. Okay. I want to go from y equals 0 to y equals root 2 over 2. So here's 1. Root 2 over 2 is like somewhere in here. It's like around 0.7-ish. So I know I'm going to want these values for y. Okay, let me label my axes here. This is x. This is y. And now I'm going from x equals y to this thing. So let me graph those. So x equals y. I know what that looks like. That's a line. Here's x equals y. And then this other thing, we have to figure out what that is. So x equals square root of 1 minus y squared. You might recognize it right away, or you might just want to do a bit of a manipulation to it. So maybe square both sides, get x squared equals 1 minus y squared, and then get x squared plus y squared equals 1. Ah, this I understand. This is a unit circle. So now I will draw a unit circle. Okay, good. It's easier if you draw the circle first and then the axes, but I didn't have a choice this time. So I want to go from, let's see, I go from x equals y up to x equals something else. So it's horizontal things. So I go from x equals y, all the way up to x equals square root of 1 minus y squared. And I do that from y equals 0 up to y equals root 2 over 2, which is actually where these things intersect. So let's go all the way. So this is my region. Cool. Okay. So the first way we could do this is using geometry. This double integral is actually just integrating 1, so it's just finding the area of the region. Can you find the area of the region? How do you do it?
Well, it's 1/8.
That's right. Yeah, it's just 1/8 of a circle. So it's 1/8 of the unit disk. So it would be 1/8 of the area of the unit disk. So 1/8 times pi times 1 squared is pi over 8. So it should come out to pi over 8. Way number one, our other way is, well, we could compute it directly. Let's do that. So, good. So compute it. So so this is implicitly integrating 1. So the integral of 1 with respect to x is x. Let me just copy the outer integral. So y equals 0 up to y equals root 2 over 2. Okay, so then I have x, and I'm plugging in x equals the top thing minus x equals the bottom thing. So I would be doing root 1 minus y squared minus y dy. Okay, now this integral. This you can do. But the square root of 1 minus y squared is not so easy to integrate when you don't have a y multiplied by it on the outside. You can do it, but you have to use a trig substitution. So you could do it, but using a trig substitution is sort of implicitly converting to circular things anyway. So this requires a trig substitution. So let's not do it. Let's try our second method, which is convert to polar, and see if that helps. Cool. And since we're converting to polar coordinates, might as well drink a polar beverage. It will help us get it right. It will help me get it right. Delicious. Okay, great. So we could go in either order, but what we want is like theta equals something up to theta equals something, r equals something up to r equals something. We're still integrating 1, and then dx dy is really dA. So now we want to integrate 1 dA. And recall, so dA is on the one side, dx dy, and it's also r dr d theta, depending on which coordinate system you're using. So for us now, it's r dr d theta. So now what's left to do is to set up our region in terms of polar coordinates. So r, let's see, r, which r's do we want? It's like, which circles do we want? So you want all the circles from a radius of 0 all the way out to having a radius of 1. So r goes from 0 to 1. And then our thetas, well, we want theta certainly starting at 0 and then going all the way up, but stopping just here. Our last time we went all the way around, so theta was 2 pi. But now theta is whatever this is. I'm tempted to say pi over 8 because it's an eighth of a circle, but no, it's pi over 4 because it's a fourth of half of the circle. Okay, so theta goes from 0 up to pi over 4. And now we have to integrate this thing. Okay, let's do it. Maybe the 1 is confusing when it's r. So there, just integrate r. Okay, so I'm going to copy theta equals 0 up to theta equals pi. And now integrate. Integral of r with respect to r. 1/2 r squared. And we plug in from r equals 0 up to r equals 1. And we're going to eventually integrate that whole thing d theta. So let's do it. Let me copy the outer integral, 0, pi over 4. Theta goes to 0 to pi over 4. Okay, if I plug in 1 here, I get 1/2. If I plug in 0 here, I get 0. So this is just 1/2 d theta. So I get 1/2 theta from theta equals 0 to theta equals pi over 4. So I get 1/2 times pi over 4, which is pi over 8, which is what we wanted. So we converted to polar and made it happen. Okay, questions or ideas? Okay, let's do another one. So let's compute. Compute, if you would, the integral from 0 to 1 of the integral from 0 to the square root of y minus y squared. What a crazy thing. Of the function 1 over the square root of x squared plus y squared dx dy. Okay. Okay. Good. So x equals. So the first thing to do perhaps is to add in what the variables are. So we're going from x equals 0 up to x equals square root of y minus y squared. And we're going from y equals 0 to y equals 1. So now we have some hope of graphing this thing. Okay, I know what the function x equals 0 looks like. X equals 0, it's a vertical line. But x equals square root of y minus y squared, we got to figure that out. So what does x equals square root of y minus y squared look like? Like what is it? Let's try to get our hands on what this is. So if you square both sides, we get x squared equals y minus y squared. So if we bring it over to the other side, we get x squared plus y squared minus y equals 0. And I'm inclined to complete the square. So I get x squared plus y squared minus y plus a fourth, I think will do the job, equals a fourth. Let's try that. So we will get x squared plus, I think, y minus 1/2 quantity squared equals 1/2 quantity squared. Okay, let's see if that works out. So if I FOIL this, so certainly x squared matches with x squared, 1/2 squared is 1/4. If we FOIL this out, we get y squared. This becomes y squared minus a half y plus a fourth. So I think that matches up with what we had before. Okay. So this is what x equals the square root of y minus y squared looks like. Can you see what this is? Yeah, you can see. A circle. Yeah, a circle. So this is a circle of radius 1/2, centered at x equals 0, y equals 1/2. Okay, so now we have some idea of what it looks like. So I'll draw the circle first. There's the circle. And it's centered at 0, 1/2 and has a radius of 1/2. So that means that the axes are down here. So this is the x-axis, and this is the y-axis, and this is the point 0, 1/2. So there's our region. And we're supposed to go from y equals 0 to y equals 1. Okay, luckily that's at the top. And we're supposed to go from x equals 0 to x equals the square root of y minus y squared. So we know that this thing is this whole curve, but we squared things at the beginning. Okay, so we only want when x is positive. So x equals the square root of y minus y squared is this part, and x equals 0 is this part, and so this is our region of integration. We're going, in each case, from x equals 0 out to the curve. Okay. So I could ask you, what is the antiderivative? Okay, now let's compute. Now that we have a picture, what is the antiderivative of this thing with respect to x? But perhaps you've guessed that, like, life would be bad. There is no antiderivative. So perhaps what we should do is convert to polar. Okay, try to get it right. So we'll want to go from theta equals something up to theta equals something, r equals something up to r equals something. Our integrand function is 1 over the square root of x squared plus y squared. Let's see. 1 over the square root of x squared plus y squared is 1 over the square root of r squared, which is 1 over r. So that's our integrand function, 1 over r. And then we multiply by dA. So dA in polar coordinates is r dr d theta. So this is our dA. Okay. Now we just need to set up our limits of integration. So I'm going to erase these horizontal lines. That's how we figured out our region. But now we want to figure out what our r's are. So our r's are going to depend on theta. So we want r to go from 0 out to whatever this curve is. Now we have to figure that out. Okay? So one way to do it is to look at the original thing. So this curve, this outer curve, was described by, well, x squared equals y minus y squared. So x squared plus y squared equals y. X squared plus y squared is r squared, and y is r sine theta. R is not 0 except at the beginning, but on most of it r is not 0. Almost all of it r is not 0. So r equals sine theta. So this whole curve can be described by the equation r equals sine theta. So we want to go from r equals 0 out to r equals sine theta. And then the thetas we want, we don't want to go all the way around 0 to 2 pi. We don't want to go just 0 to pi over 4. We want to go 0 to pi over 2. So theta goes from 0 to pi over 2. So this one was a bit tricky to set up because first of all, we had to figure out what the thing looked like, and to do that, we had to complete the square. And then secondly, we had to figure out the equation for this circle in polar coordinates. And we had to do this little trick. Yeah. Questions or ideas about how to set it up? Okay, now we just do it. We don't know what the answer is going to be. Okay, I'm going to erase this so that I have a bit of space to compute the thing. Last time we knew that our answer was going to come out to pi over 8, but now we don't know. But I think we can guess that our answer is going to be positive, because 1 over r is always positive, and our region has positive area. So for sure we expect an answer to be positive. So let's do this. So this is the integral from theta equals 0 to theta equals pi over 2. This function, and then from r equals 0 up to r equals sine theta. And then 1 over r times r is just 1. So these cancel out. And then dr d theta. So let's do it. The integral of 1 with respect to r is just r. Let me copy the outer integral, theta equals 0 up to theta equals pi over 2. And we're doing r from r equals 0 to r equals sine theta. We'll eventually integrate that d theta. So this is just sine theta. So we're going from theta equals 0 to theta equals pi over 2, integrating sine theta d theta. Integral of sine theta, cos theta, negative cos theta. You remember? Negative cos theta. Yeah, negative cos theta. Because when we take the derivative of cos theta, we get negative sine theta. So then negative sine cancels that out. And we go from theta equals 0 up to theta equals pi over 2. So we get negative cos pi over 2 minus negative cos 0. So it's 0 plus 1, which is 1. Okay, which is a positive number as we expected. Okay, so we went from having this impossible integral that we couldn't do, that was even a bit tough to decipher, to drawing the picture and figuring out how to set up the integral to getting an answer of just. Yeah, questions or ideas? So one thing you might be thinking is, gosh, that was lucky that we were able to figure out what dA is in terms of r and theta. Maybe, okay, so I won't pretend like you would be thinking about this, but this was one way of changing variables, changing from rectangular xy to polar coordinates r theta. And we were able to do this cute little thing where we drew the circle and we found the area of the thing in terms of r and theta and dr and d theta. And we can usually do that. But here's a way that generalizes to all kinds of changes of variables, which is to use linear algebra, that tool you have in your pocket, that you have brought into this class and that we will use whenever we need to. So another way to derive dA is r dr d theta. So we did it drawing a picture of a little sector, and I will do it some other way. So we want to view this process of transforming back and forth between xy coordinates and r theta coordinates as a linear transformation. So linear transformations are things that you studied in linear algebra, like matrices are linear transformations. So we imagine that we have the r theta plane, which is a bit abstract, and you have some little dr here, which I'm exaggerating, and you have some little d theta here. So this little thing here is dr d theta. That's just dr times d theta. That's the area. And then you also have over here the xy plane, where dx, here's dy, and here's this little box, dx dy. And you imagine that you have a transformation that maps the r theta plane to the xy plane. So if you had any sort of a little region in here, it would map it over to a little region in there. But we want to understand like what's going on in a linear way, so we could find a best linear approximation of that by using the Jacobian. This is something that we did a few weeks ago. So the Jacobian would be the linear transformation. Of course, this actual transformation would bend things and make them curvy, but we can imagine the linear transformation with the Jacobian dt. And actually, we know what the transformation is that takes us from r theta coordinates to xy coordinates. So we want a transformation that takes us from r theta coordinates to xy coordinates. So all you would have to do is do t of r theta. We want this to give us x. X is just r cos theta. And we want it to give us y, which is r sine theta. So that's actually how you get from one to the other. You have a point in r theta space. You just do r sine theta, r cos theta, r sine theta. You get a point in xy space. There it is. So we want to use the Jacobian matrix dt because it's the linear transformation that takes the linearization of this transformation. So the idea is that this little dA, let's see, that the dA is the determinant of the linear transformation times the old area gives you the new area. So we want to know if we have some old area in the r theta plane, what do we have to multiply it by to get our new area in the xy plane? So this is in the r theta plane, and this new area will be in the xy plane. And to translate between them, you use the determinant of the Jacobian matrix, which tells you how much things were stretched. So if the transformation was just like multiplying everything by 2, well then your areas would be twice as big on the other side. So the determinant of your stretching matrix would be 2. So let's figure it out. So we can write this down, dt, just to remind you, it's the partial derivative of the first function with respect to the first variable, and the partial derivative of the first function with respect to the second variable, partial derivative of the second function with respect to the first variable, partial derivative with the second function with respect to the second variable. Nope, that's a y. So this here, this is like f1 of r and theta, and this is like f2 of r and theta. So let's do it. So derivative of this function with respect, these weren't x's and y's. These are r's and thetas. I was going to be hard pressed to take the derivative of this with respect to x. Okay, sorry about that. Okay, so the derivative of this function with respect to r is just cos theta. And its derivative with respect to theta is negative r sine theta. I think that's right, negative r sine theta. The derivative of the second function with respect to r is sine theta. And its derivative with respect to theta is r cos theta. Okay, so there's the Jacobian matrix. And now let's take the determinant. So to remind you, to take the determinant, you do like the positive diagonal product minus the negative diagonal product. So this times this minus this times this. So we get r cos squared theta minus negative r sine squared theta. So this is r times cos squared theta plus sine squared theta, which is just r. So it tells us that if we have some old area, so where shall I write this? I'll write it over here. So dA, so it tells us that you take the old area, you multiply by the absolute value of the determinant of dt, and it gives you the new area. So here's the new area. So it will give you dx dy. The old area was dr d theta. And it says what you have to multiply by to turn your dr d theta dA into a dx dy dA. Well, the determinant of dt was just r. So it's r. So this tells you that, dA is this thing, r dr d theta. So clearly in this case, this method was maybe not as user-friendly as just drawing the circle and finding the area of the little piece. But this method, it's nice to have two different methods of deriving something because sometimes one is useful for more things. This one is going to generalize to other kinds of changes of variables.